I'm Anil Kumar. Welcome to our new website, Global Math Institute. We are going to discuss test papers from students all over the world. We are going to share with you what everyone is doing in different parts of this globe. And I hope that is going to help you a lot. Here is a test paper from one of my students in Canada, grade 7. We'll talk about patterns in whole numbers. So there are about 9 questions in this test paper where we look into greatest common factor, lowest common multiples, and related questions. You can see first 4 questions now. You can pause the video, copy these questions, try them out. Here are other questions of this test paper. Question number 5 to 8, and then the very last question which deals with patterns. Let us see how to solve them one by one. First question here is, find the greatest common factor, GCF, of each pair of numbers. Use different methods. The first one, the two numbers are 16 and 8, right? So when you have numbers, one is 16, the other one is 8, right? What you notice, we know 8 is a factor of 16, all right? Or you can say 16 is a multiple of 8. So in this case, for sure, the greatest common factor should be what? It has to be 8, right? Greatest common factor. Factors are smaller numbers, right? So we have our answer 8, since 8 is a factor of 16 itself, right? So that is one way of doing it. The other way is to write factors, right? So we can write factors of 16. So we know 1 is a factor of 16. 1 times 16 is 16, correct? And then we know 2 times 8 is 16. And we know 4 times 4 is also 16. So these are the factors. As far as 8 is concerned, we know 1 times 8 is 8. 2 times 4 is also 8, right? Well, that gives you all the factors, and which is the greatest common factors. Well, you know the common factors, correct? So these are common factors. These are all the common factors. Amongst the common factors, the greatest common factor is 8, right? So we can say, confirm again that GCF, the greatest of all these common factors, is 8. Does it make sense to you? Correct? So that is the second way of doing it. Perfect. Now let's take the next example. I'll give you 3 different methods for sure. So the first way, and this is the second way for the first question, we'll elaborate more on different methods for example B and C. So now let's look into the factors of 10 and 35. So as far as 10 is concerned, the factors of 10 are, we know 1 times 10 is 10, and then we know 2 times 5 is 10. As far as 35 is concerned, 1 times 35 is 35, and 5 times 7 is also 35. So if you match this, what we see is 1 is always a common factor, correct? And the other common factor is 5. So these are the 2 common factors, out of which 5 is the greatest common factor. Correct? So this time we did this using the second method. Let me take opportunity to discuss the third method with you now. So we are looking into 2 numbers, 10 and 35. So we'll write down their prime factorization. 10 can be written as 2 times 5, and 35 can be written as 7, and 5. So this is prime factorization, correct? So what you got here is prime factorization. Now you can see from here that actually the common factor between them is only 5, and therefore that is the greatest common factor. We can actually combine it with the Venn diagrams, right? So let me draw two Venn diagrams. Let me draw one Venn diagram with two circles. So here we will write factors for 10, 5 being common. So 2 and 5 is common, correct? And that is for 35, 7, correct? So what you see here is that we have written the factors for the numbers 10 and 35, correct? The greatest common factor is 5. Do you see this number here? And so once again, we confirm that 5 is the greatest common factor. So that becomes your third technique to find the greatest common factor. For bigger numbers like 72 and 40, this is a very good technique. For smaller numbers, you can list all the factors and match. Perfect. So you can follow any of these techniques. I'd like you to now pause the video and apply the best suitable technique for part C, where we are looking into numbers 72 and 40. Well, of course, for 72 and 40, these are big numbers, right? So let me do prime factorization. So we'll do prime factorization. And then we'll use Venn diagram. Is that clear to you? So as far as 72 is concerned, we have the numbers with 72 as prime number 2 can get into this. So 2 times 36, correct? So for 36, we can again split this, taking a prime number 2 times 18, and then with 18, we have again prime numbers 2 is a factor times 9, and as far as 9 is concerned, I could write 9 as 3 times 3. You see that? So 2, 2, 2, 3 and 3 are the prime factors for 72. Let us do the same for 40. Correct? So as far as 40 is concerned, we know 2 times 20 is 40. And then 2 times 10 is 20. So if I write like this, I kind of organize as I move. So this is a neat technique, right? So with my experience, I found that factoring and displaying the data in this fashion really helps, correct? Now we'll use the Venn diagram. So we'll write factors of numbers 72 and 40 in a Venn diagram, right? So we'll write down 40 on this side and 72 on this side. We'll work with the common factors. How many 2's? 1, 2, 3 2's, 1, 2, 3 2's, right? So we could write this number 2 cube here. 2 cube is 8, right? So which is basically what I'm writing here is 2 times 2 times 2, which is 8. Do you see that? So we have already taken care of these 3 2's. We're left with 1 5 for 40. And here we are left with 3 times 3, right? So we are left with 3 times 3, which is 9. Do you see that? So from here clearly, we get our result that the greatest common factor is 2 times 2 times 2, which is 8. So in the Venn diagram, you see it right in the middle as shown here. So you see there are a couple of ways of finding the greatest common factor. Globally, we use different methods. You can adopt this last method of prime factorization in Venn diagrams, especially when we are working with bigger numbers. I hope that makes sense. So we'll take a small break here. I hope this concept of finding greatest common factor in many different ways is absolutely clear. Snow in Canada. So the question number 2 here is, find the LCM of each pair of numbers. Use different methods. 7, 9, 12, 10, 14, 8. So these are 3 sets of numbers for which you have to find the LCM. You can always pause the video and answer the question. So let's begin with the very first one, where we have 2 numbers, 7 and 9, right? What do you notice? Well, we know that 7 is a prime number. Since 7 is a prime number, the lowest common multiple will be the product of the 2 numbers given to you, especially when the other number is not a multiple. And we also notice that 9 is not a multiple of 7, and therefore the LCM in this case is 7 times 9, which is 63. Is that clear to you? So if there is one prime number, you check whether the other number is a multiple or not. If the other number is not a multiple, then their product is the lowest common multiple. Perfect? Okay. Now let me tell you why. Now, if the case could have been, let me give another example here. If the numbers were 7 and 21, correct? So in this case, LCM is what? So LCM in this case is 21. Reason being that 21 is multiple of 7. Is that clear to you? So you see the difference between the given example and the note which I have added here at the end. So I hope this concept is clear. So if there are 2 numbers, one of them is a prime number, then the LCM is either the other number, the bigger one of those, which is the multiple, or just the multiple of both, right? So that is what we'll do. Right. Now let's look into the second example, which is we're talking about 12 and 10. Yes, we have to use different methods. We'll teach you different methods also as we move along. So this time, when we have these 2 numbers, we will use the concept of Venn diagrams. So we'll combine prime factorization and Venn diagrams. We can actually use this concept to find both greatest common factor and LCM. So let's do prime factorization of the numbers 12 and 10. As far as 12 is concerned, I could write this as multiple of 2 and 6. 2 is a prime number, so we're trying to take prime numbers as one of the factors. And 6 is 2 times 3. As far as 10 is concerned, we could write this as 2 times 5. What do you notice? Well, let's make a Venn diagram to represent the prime factors of the given numbers. The common numbers are 1, 2 is common, right? So let me write that in the middle. So 1, 2 is common. What remains here? For 12, 2 and 3. For 10, the number 5. You see that. So this is for 10, this is for 12. Now from here, what is the lowest common multiple? Multiples are bigger numbers, right? Just multiply all these numbers. So we'll do 2 times, 3 times, 2 times 5 to get our answer, which is 10, 30, and 2, 60. Do you see that? So using prime factorization and the Venn diagrams, we can easily find the lowest common multiple. Do you see that? Right. Now, we'll talk about the third method, which is what we have learned in our childhood. It is a special kind of division. We call it ladder division. So, in ladder division method, we actually, here's a technique, right? So, write the two numbers given to us, which are 14 and 8. And we try to figure out what are the common factors for these. So 2 is a common factor. So 2 goes 7 times in 14 and 4 times in 8. Now they have no other common factor. So from here, we can write down that the LCM is equal to 2 times 7 times 4. So 8 times 7 is your answer, right? So 8 times 7 is 56. So that is our answer. So 56 is LCM of 14 and 8. Is that clear to you? So I hope with this, how to find LCM between two numbers is absolutely clear. You've learned different ways of finding the common multiples. The first method was to list all the multiples, right? And then get it. So for example, I could have gone like 7, 14, so on, all the multiples, right? So we'll get definitely 63, right? And then 70 and so on. As far as 9 is concerned, we could have written 19, 18 and so on. 63 was common, right? And then we have 72 and so on. So when you list all the common multiples, the first one common becomes your lowest common. This was a special case where one of the numbers was the prime numbers, and therefore we derived at the result very fast just by multiplying the two numbers. Note that the second number was not a multiple, and therefore we had a very big number. If the second number is a multiple as taken in this example, 7 and 21, then the multiple is right there before you, right? So the lowest common multiple is the other number, right? Then you learn the technique of prime factorization combined with Venn diagrams to find LCM. Here you can also write down the greatest common factor, which was 2, common to both. And then we learned ladder division, which is excellent method, especially when you have many big numbers. I hope that helps. Here is question number 3. Frances has piano lessons every 4th day. She has ballet lessons every 5th day. She has soccer every 2nd day. On which day will she have all 3 activities? Explain. Now to answer these questions, we need to really figure out what is the lowest common multiple, right? So what we are looking for here, all together, we are looking for lowest common multiple, right? So next day, multiples are always bigger numbers, which is common for all. So let's begin with the piano lessons. Let's call this as, let's say, piano. Now, piano lessons are every fourth day. That means on the fourth day, then multiples of 4. So it will be 4, 8, 12, 16, 20, 24, and so on. Now, she has ballet lessons every fifth day. So let's say ballet. So ballet lessons every fifth day means 5, 10, 15, 20, 25, and so on. She has soccer every second day. So from the first two, we see there is common multiple 20. Now every second day means all even numbers, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, and we again get 20, correct? So clearly, we see that the lowest common multiple is indeed 20. And therefore, for this, our answer is on the 20th day. Is that clear? So that is how we can actually find answer for such questions. Now let's look into question number 4. Find the square of each number. Now we need to find square of 12, that is to say 12 square. So you can multiply 12 with 12 and what you get is 144. So that becomes your answer. Well, if you remember the squares, it is always good. Otherwise, you can do it on the side. So for example, we can say 12 times 12. First multiply by 2, so we get 24. Then 1 is in tens place, so you have to put a 0 here, and then you get 12. And adding them, we get 144, correct? The next number is 15. We need to find square of 15, right? Now to find square of 15, you can do the same thing, 15 times 15. 5 times 5 is 25, 5 times 1, 5 plus 2, 7. And then with 10, this 1 means tens place. So we get 150, and when you add them, you get your answer, which is 225. So this is 225. So that is the square of number 15. If you have to find a square of 1000, that is, you need to find what is 1000 square equals to, you'll have 3 zeros more, right? 3 and 3. So it is 1000 and 3 more zeros. 1000, which is 1 million, right? So that is how you can actually estimate, rather write the correct answer. Question number 5. Find the square root of each number. Now we are given the number 196, 401. I'd like you to pause the video and write down the square root of these numbers. Well, 196 is more than 10 square, right? 10 square is 100. It is more than 10 square. And we also see that it is less than 15 square, 225, right? 225. It is less than 15 square, which is 225. The number ending with 6. So when do you get ending of 6 in a square? Well, you know 4 square is 16. So the number ending with 6 is when we have 4 square, correct? Then you get 16. So the number in between, which could be the square root of 196, is 14. It has to be more than 10, right? So we can say square root of 196 is equal to 14. So we kind of estimate it. So if you don't know the exact value, then you can estimate just as we did. I will also teach you a method of finding a square root with a special division, right? So we'll talk about this later. Now let's find square root of 400, right? So square root of 400. You could write this as square root of 4 times 100. Square root of 4 is 2 and square root of 100 is 10. So we could write this as 20. Square root of 1 is the number 1 itself, right? We can also find square root using prime factorization, right? So there are many methods. If we have big numbers, we can use prime factorization to find square root. So let me write it down here. Some of you can explore this method of prime factorization for square roots. We'll take this up also separately at the end. Here is question number 6. A drawer is divided into 12 congruent sections. The drawer has total area of 432 centimeters square. What is the side length of each section? So let's say this is our drawer. So drawer is kind of a tray which you have in the cabinets, right? And this is being divided into 12 congruent sections, right? So this drawing is not to the scale, but think like this, that we divide one portion into 4 parts, for example, okay, and this into 3 parts. Let us say it was a rectangle, we divide into 12 congruent squares as shown here. Now let's try to understand the question. It has a total area of 432. So area is 432 centimeters square. It is divided into 12 congruent parts. So let's divide this area into 12 parts. So each small area is 432 divided by 12, right? So the smaller area will be 432 divided by 12. Now easy calculations, you can divide both the numbers by 4, for example, 3 times. 4, 1, this does not go, 8, 408. And now we can divide by 3, right? 3 times 1 and 3 times 3 is 10 and 6. So we get the number 36. So that is the area of each square, right? So what is the side length of each square? Let's say x is the side length of each square, right? Let us say. So we know that x square is 36. That means x is square root of 36. And that is the number 6. And the units are centimeters. Do you see how we found it? So what we have done here is that first step, we divided the total area 432 into 12 equal parts, right? Which came to be 36. Now 36 is area of each square. So square centimeters, right? So the dimensions will be square root of 36, which is 6. So each side of the square is side length is 6 centimeter each. So that is how we will get the side length of each section. So I hope this concept is absolutely clear, right? So it's a very important question. Try to understand it. And that is how you could think about its solution. Now I purposely saved this space and we'll discuss how to find square root with prime factorization. So we'll take the number 196. So let's do the prime factorization of the number 196, right? So we're trying to figure out what are the prime factors. So let's divide it by 2 first. So half of 196 is what? So 9 times 18, right? And then this 8. And now this is also even number, so we can further divide it by 2. So when you divide this by 2, you get 2 times 4 is 8 and 18 9 times. 49 is 7 times 7. So you see 196 is equal to 2 times 2 times 7 times 7, or 2 square times 7 square. Do you see that? Or you can say this as 14 square. So that is how we can use prime factorization, and so we can write that the square root of 196 is equal to 14. Do you see that? So that is the concept, and prime factorization is a very good method to find the square root. So if you don't remember square roots of some numbers, you could easily do prime factorization and get the answer. Question number 7. Write these numbers in order from least to greatest. 4 cube, 5 square, 2 to the power of 4, 3 to the power of 5. Now in this, we don't really have any tricks. Let's just find the value, right? So 4 cube is 4 times 4 times 4. 5 square is 5 times 5. 2 to the power of 4 is 2 times 2 times 2 times 2. And 3 to the power of 5 is 3 times 3 times 3 times 3 times 3. You need to calculate these values. And once you calculate, then you can easily answer this question, right? So 5 square, is 25. 4 square is 16. 16 times 4, right? That gives you the answer for 4 cube, right? So 16 times 4 is 64. So we get that number as 64. Now 2 to the power of 4 is 4, 8 to 16. And 3 to the power of 5, 3, 9, 27, 81 times 3, right? So we can say 81 times 3. 3 times 1 is 3, 3 times 8 is 24. So you get your numbers, right? Now you can write these numbers in order from least to greatest. So least among them is 2 to the power of 4, right? So we get 2 to the power of 4. And then we get 25, which is 5 square. And then it is 4 cube. And then it is 3 to the power of 5. Do you see that? So that is how we can find the solution of this one. Question number 8. Write each number in exponent form in as many different ways as you can. Now that is a very interesting exercise. So I'd like you to pause the video and then answer this particular question. Now to give all the possible ways of writing it, prime factorization is indeed a very good method, right? You could straight away also write this. 625, every number can be written as to the power of 1. That is also exponential form, right? Square root of 625 is number 25. So we can write 25 square. Now 25 is 5 square, and therefore we can write this as 5 to the power of 4. Perfect. So that is how you could actually systematically get to the square root of 625. So I hope that is clear, right? Now let's look into 256. We'll adopt a different method. So we'll do prime factorization to get the exponential form of numbers giving 256. Let's divide by 2. So 2 times 1, and then this is 2 times 2 is 4, and 16 is 128. And now again, half of 128 is 64. Half of 64 is 32. Half of 32 is 16. So likewise, do you see how we could write 256 as a power of 2, right? And as far as 16 goes, it is 2 times 8. 8. Okay. Is written as 2 times 2 times 2, correct? So we have so many 2's. When they multiply, we get 256. Let's count. 1, 2, 3, 4, 5, 6, 7, 8. So 256 is 2 to the power of 8, as you've just seen. Correct? Now, you could group them in 2 2's, right? So it could be written as 4 to the power of what? Half of 8, right? So if I group them into 2 2's, we get groups of 4, and we'll have 4 of them. Correct? We have 4 of them. Now, if I group them into groups of 3, can I group them? No. So we have 2 to the power of 8, we get 4 to the power of 4 as 256. So total number is this, and half of 1, 2, 3, 4. If I group 4 of them together, so we'll have 2 groups of that multiple, right? 2 to the power of 4 each. So what is 2 to the power of 4? So it is 2, 4, 8, and 2, 16. So we could also write this as 16 square. And of course, we can write 256 to the power of 1 as the next option. So I hope this concept is absolutely clear, and I hope you understand how prime factorization can really help us to find square roots of number and also to write numbers with different exponents or index. Now let's take up the last question. Question number 9. Find the next 3 terms in each pattern and then describe each pattern in words. Write the pattern rule. So it has 2 parts. One, you have to find the terms and then describe it using pattern rules. I'd like you to pause the video, answer this question, and we'll take a short break. We had a massive snowfall in Canada. Let's enjoy some snow for a moment, and then let's get back to this question on pattern rules. Question number 9 is from a test paper. We have already discussed 8 questions of this question paper earlier. So the question here is, find the next 3 terms in each pattern and then describe each pattern in words. Write the pattern rule. So let's begin with the very first one, which is 4, 7, 10, 13. Now to find the pattern and write the next 3 terms, which is the first part of it. It says find the next three terms, right? So what we should do? We should see how it is growing. It is definitely growing. So from 4 to 7, we are adding 3, and then again we are adding 3, and this process is repeated. So every time we are adding 3 to get the next number. So if I add 3 to 13, then what will I get? Well, 13 plus 3 is 16. And then again, if I add 3, then I get 16 plus 3, which is 19. And this process should be repeated, right? So we again add 3. So that is the process, adding 3 each time to get the next number. So we get 22. Do you see? So that is the first part, which says the next three numbers, right? So the next three numbers are as shown 16, 19, and 22. Now, second part of this question is then describe each pattern in words. Right. So now we need to describe the pattern, correct? So to describe the pattern, what should you do? Well, the important criteria is always write down the first term. So you can start at 4, and then what do you do? Then you add 3 each time. Is that clear, right? So that is how you can describe the pattern, correct? So sometimes we can also write a pattern rule, right? So in this case, I will mention the pattern rule also. So let's see, what is the pattern rule here? Now, this is called the term number. So here this is our first term, this is the second term, third term, fourth term, fifth term, and so on. Since we are adding 3 each time, adding 3 is like multiplying 3, right? So we are adding 3 in the first term to get 7. So in the second term, 3 is added only once, right? So what do? You have to multiply by 3 times 2 to get this number, right? So what we notice here is that when I do 3 times 2, I get 6, not 7. How do I get 7? I get 7 by adding 1, right? So pattern rule for nth term, we say, is 3n plus 1. So if n is 1, so we get 3 times 1, which is 3, plus 1 is 4. 3 times 2 is 6, plus 1 is 7. So like this, we can do the rule. This rule is called explicit pattern rule. For patterns which are simple, as shown here, you can always write very easily explicit pattern rule, right? Now, it is not always easy to write. Note that. So we've done part A, and now let's take up part B. So I hope the concept is absolutely clear, right? Now the question for us is a pattern which is 3, 8, 5, 10. How do we get the next 3 terms for this? That is very tricky. Now, 3 to 8, the difference is how much? Well, we are adding 5. And as far as 8 to 5 is concerned, we are adding only 3. So we are not adding the same number. Here, what are we doing? 5 to 10 is adding 5. So we kind of get our pattern, right? So we can say that add 3 and 5 alternately. Does it make sense to you? Well, that is one way, definitely, to describe our pattern. So it is kind of two-step process. So what we'll do here is that we'll add 3. So when you add 3, you get the number, which is 10 plus 3 is 13. And then to get the next number, we will add 5. And 13 plus 5 is 18. Do you see that? And to get the next number, we'll again add 3. And we get the number 21. Do you see that? So we followed this process. And based on what we did, we can say that the next 3 terms are 13, 18, and 21. And you can follow this process. Does make sense to you? Correct? Now this is a slightly difficult pattern to describe. Anyway, let us make an attempt. How do we describe it? Well, we can say start at 3, add 5, then add 3. Do you see that? So start at 3, add 5 to get the next number, and then add 3 to get the next number. So basically, alternately, add 5. We are doing 5 first, right? And 3 to get next number. So that becomes our rule. Does make sense to you, right? So we could write like this, so that becomes our rule. So start at 3, add 5, then add 3, and alternately add 5 and 3 to get the next number. Perfect. So sometimes we may have to describe in the fashion given, right? Now let's move on and take the next 2 questions and see how to describe those types of patterns. Nine C is the numbers given to us are 66, 65, 63, 60. In this case, it is a decreasing pattern. To go from 66 to 65, we take away 1, and then we take away 2, and then we take away 3. That means for the next number, I should take away 4, and then I should take away 5, and then I should take away 6. So we get our next numbers as 60 take away 4 will be 56, and 56 take away 5 will be 51, and then take away 6 will be 41. So we can write down that the next 3 numbers are 56, 51, and 45. How do you describe this rule? Well, to describe the rule, what we observe here is that we start at 66, then subtract 1, then 2, right? So basically what we are doing is subtract 1 more each time. Is that clear to you? So we alter, in this case, each time we subtract 1 more number, right? So you can say that the rule is start at 66, subtract 1, then each time increase the number subtracted by 1. So that is another way of saying the same thing. So write down the way which you feel comfortable with. I hope you got the idea, right? The last one here is the number pattern 3, 5, 10, 18. Now here, what do you think is happening? Well, let's check. 3 to 5, we added 2. And 5 to 10, we added 5. And then we added 8. So this time, what we observe here is that we are adding 3 more each time, right? So you see, it is increasing by 3 more each time. So if you go with this kind of a thing, then next time we have to add what? 11, right? So if you add 11 to 18, you get 29, right? So likewise, you can expand. And this time, we have to add what? Well, 3 more than 11, which is 14. And when you do so, you get 4 plus 9 is 13, and then 43, right? And next number to be added is 3 more than 14, right? Which is 17. Adding 17 to 43 will give 7 plus 3 is 10, and we get 4 plus 1, 5, and 1, 60, right? So these are the numbers. So we can write down that the next 3 numbers are 29, 43, 60, right? So slightly tricky, right? How will you describe this? So we can now same type of description as we did before. We can say start at 3, add 2, then each time increase the number to be added by 3. Does it make sense to you? So that is how you can actually describe this particular pattern. I hope that makes sense. So with this we conclude the video, and you will see that in this video we had very interesting examples where different numbers were added at different times to get the next number. I hope you find it interesting and useful. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'll be great. Thanks for your time and all the best.